Good morning. I wanted to share some ideas about these topics of voltage and current because they can really sound like the same thing. So I wanted to do some demonstrations with you, and I'll start by sharing my screen. This is from a simulation called PHET Circuit Construction Kit, and there are links to it on Canvas. We'll be using this as one of our lab tools later on. But you can see I built a circuit, and this particular circuit has a 12-volt battery driving a light bulb and another light bulb, and this one has twice the resistance that this light bulb does. Then we come over to this circuit, and now this is set up in a slightly different arrangement, but all the cast of this scene are the same, with a 12 battery and then two light bulbs, 4 ohms and 2 ohms. But you can see they're very different. So why is it that they're so different? And then how can we use the terms of voltage, current, and resistance, and by the way, power, to describe why they look different? So we can see that the rays of light are supposed to indicate how bright they are, and brightness is going to correspond to power. All right, well, we have some tools here too. So I'm just going to grab this ammeter and we'll bring it over here. Actually, we go to the advanced column. Um, Maybe I'm not going to do the ammeter right now because there's a separate one that's a con non-contact one. This one I'd have to break the circuit and stick it in there for you to see what it looks like. And then we have voltage. So let's go ahead and just check this out. You know what I'll do? I'll just grab this ammeter and we'll put it in a more generic sense. So, all right, let's take a look. So I'm going to use our voltmeter, and this is measuring the potential difference between two places in our circuit. Okay, and that's 12 volts. That means that the red side here has a higher electric potential than the black side by an amount of 12 volts. And we can come down here and check this out. That's also 12. But then we can contrast that with this other kind of circuit. So I get 12 there. But then when I look at the individual parts, here I get 8. And then here I get 4. Oh, right. So 8 plus 4 is 12. That makes sense. Okay, and now let's get rid of the voltmeter. And in order to use the ammeter, what I'm going to have to do is to break the circuit. So I can right click on this joint. Oops. Double click on it. Let's stick my ammeter in. You notice when I broke the circuit, no current flowed. So now I'm getting 9 amps worth of current, and that's a lot. So this refers to the speed of the charges as they zip around. And of course, it's worthwhile mentioning that this is the direction of electron flow because electrons are the only charged particles that are moving in the circuit. And that's because they're loosely held valence electrons. So if you think about a copper atom, copper is going to have a whole bunch of electrons, most of which are pretty tightly held by the nucleus. But there are a couple of orbits that are way out there, and they are more loosely held. That's what makes copper a good conductor. So while we're at it, we can grab another ammeter, and then I'm going to break this circuit, and we'll stick the ammeter in here. Now, and that says only 2 amps. Okay, good. Now I'm going to skip over to a couple of slides that help tell us about what a model might look like. Because one of the things that we have to do is come up with some kind of rationale about these words like Energy, charges, voltage, current, and power. We need to come up with a model because this is all happening inside wires that we can't see. So this is a classic distribution network. And what I wanted to show you is that we can imagine a model of a distribution network and then apply those concepts to electricity in a way that can help you visualize what's going on. So in this column, as we walk down through, our distribution network means that we have some kind of consumable and we have some way for the consumable to get to where it's going to be consumed. So I'll call that a carrier. And then our carrier is going to have a certain degree of capacity. And then our carriers are going to move with a particular speed. And then the combination of all those winds up becoming consumables delivered over time, or consumables, whatever is consumed per unit time. And so that's the measure of our distribution network. So my model is Amazon, and the consumable are packages. So every morning, trucks get loaded up with packages, and then the delivery trucks go out and start distributing those packages. So the carriers are obviously trucks. Now, here's the interesting thing. So when they're going to get loaded up, then we have a certain number of packages per truck. And as the trucks circulate through their route, they're going to drop off packages at all their stops. And by the time they're all done for the day, the truck should be empty. Now, the speed of those trucks, we could call it trucks per day, is our way of measuring how we're going to be able to get the job done and getting all those packages out. So ultimately, the measure is packages per day. And you can see if I multiplied packages per truck times trucks per day, then I get packages per day. So that's a good way to measure the output of your distribution network, is to multiply these two things together. Now, from an electric point of view, here we go. The consumable is energy, and the carrier are charges. And here's where we see those words voltage, current, and power show up. So voltage is the energy that each charge carries. And then current is how fast the charges move. And you can see if we multiply these two quantities together, energy per charge times charge per second, we get energy per second, which is power. And then power multiplied by time would give us the total amount of energy. So here are our key equations. So power equals voltage times current, energy equals power times time, and then resistance is voltage divided by current. This is sort of our proportionality. Now, when we see multiple consumers, they could either be set up in series or in parallel. Series is a single path, parallel are multiple paths. But our generalizations that we make is since there's only a single path, then the current has to be the same through all. And then the voltages are going to add so that the total amount of voltage drop is going to be the same as whatever the charges started with. But in simultaneous circuits, where this means that the current splits up and goes through multiple pathways, the voltage drop is going to be the same. And then the generalizations that we can make there is that the voltage drop across each component is going to be the same, but current's going to add. So in our discussion board, what I'm going to ask you to do is to come up with your own analogy. So try and fill out this part and then come up with a simple example that folks can comment on. Okay, let me go back to, and we'll see how this works. So back to circuit construction kit. The current flowing through this circle, first of all, we want to identify if this is series or parallel. Does it have multiple pathways? And the answer is yes. So that means it's parallel. It's a parallel circuit. So the voltage drop across the light bulbs is the same. And we already verified this, right? So I brought in the voltmeter and we can check it. You know, we talked about how if these are really good conductors, there should be no potential difference between the two ends because they don't take energy away. And then I go down here and I get the same thing, 12 again. All right, so we kind of guessed that that was going to happen. This bulb is the brightest. Now we have a total of 9 amps flowing through the circuit altogether. So here's where our trucks pick up the packages, and 12 volts means every truck is going to have 12 packages. And the trucks leave the factory or the warehouse, and then some go along this path, and they're going to drop off all 12. Some are going to go along this path, and they are also going to drop off all 12. But since there's less resistance here, we're going to see the trucks move faster. You can see the blue dots are going faster than up here. So 12 volts divided by 2 ohms gives me 6 amps. And here, 12 volts divided by 4 ohms only gives me 3 amps. That's why this is the brighter light bulb, and the total amount of current is 9. Now here, the diagram on the right shows a single pathway, and both bulbs are much less bright. If we trace this down through, once again, we can use the voltmeter and see what's happening. Right, so I get 8 volts here. And then I get 4 volts here. So the voltage drop across the 4 ohm light bulb is twice as much as the voltage drop across the 2 ohm light bulb. And then why is that? Well, one of the things is that we're constrained to have only 2 amps go through the circuit. Why? Because of the effective resistance. So charges have to tunnel their way through this light bulb, and then they have to go through this light bulb. That means the current is the same. You notice that there's no place where any of the blue dots are going faster than anywhere else, and that's why the current is 2. Now, voltage is current times resistance, so 2 times 4 is 8, and 2 times 2 is 4, of course, and 8 plus 4 is 12 volts. Okay. Well, I hope that helps a little bit. And what I would like you to do on the discussion board is to think about your own model. What are things that you could use to describe your own distribution network? I took an easy one, which is Amazon, but it's anything that something gets picked up and then routed to different locations. So that would be your theme. All right, and I'll have more detail about this in the actual discussion board post. But thanks for listening.